On a July afternoon in central Texas, a concrete highway slab launched itself into the air like a trapdoor, had been sprung from below. The crack was audible from hundreds of feet away. Chunks of pavement skidded across lanes. Drivers swerved. Nothing had detonated. No gas line had ruptured. No device had been planted. The cause was heat, physics, and a pressure that had been building invisibly for hours beneath the surface of a road that millions of people trusted without a second thought. And buried inside that event was a mechanism most people never consider. Water, trapped beneath the pavement, cooking into steam until the road above it had nowhere left to go. That detail alone changes how you understand what a road actually is and why. As summers grow more extreme, failures like this one are becoming harder to dismiss as flukes. Roads are not passive objects. They are engineered systems designed to absorb, distribute, and survive stress. And for most of their working lives, they do exactly that. Asphalt roads are built from a mixture of crushed stone, sand, and gravel bound together by bitumen, a dense petroleum-derived material that holds everything in place. Concrete roads use a cement matrix reinforced with aggregates and, in modern construction, steel rebar. Both materials are designed to handle daily temperature swings, the weight of heavy vehicles, and years of freeze-thaw cycles. The engineering behind a road surface is more sophisticated than it appears from a car window. The problem begins when temperatures exceed what the design anticipated. Climate change is not a future concern in this context. It is already reshaping the thermal environment that roads operate in. The 10 hottest years on record have all occurred since 2010. Heat waves that would have been statistically rare a generation ago are now arriving more frequently, lasting longer, and reaching higher peak temperatures. Infrastructure built to handle conditions from the 1970s or 1980s is now being asked to survive conditions those engineers never modeled. Aging roads, deferred maintenance budgets, and a changing climate are converging on the same pavement at the same time. Asphalt is the first material to show the strain. Bitumen has a softening point of roughly 50 degrees Celsius, around 122 degrees Fahrenheit. Above that threshold, it stops behaving like a rigid binder and starts behaving like a very thick liquid. The aggregates it holds together begin to shift. The surface ruts under tire pressure. In Phoenix, Arizona, summer road surfaces regularly reach temperatures that would be considered extreme by any standard, because asphalt absorbs solar radiation with remarkable efficiency. The surface of a dark asphalt road on a hot day can run 20 to 30 degrees Celsius hotter than the surrounding air. When air temperatures hit 43 degrees Celsius, the road beneath your tires may be sitting at 70 degrees or above, well past the point where bitumen maintains its structural grip. The result is visible deformation, bubbling, and in severe cases, a surface that shifts and separates under load. Polymer-modified bitumen exists specifically to address this vulnerability. By blending synthetic polymers into the bitumen, engineers can raise the effective softening point and make the binder more resistant to heat-induced flow. The reason this matters economically is direct. A road surface that fails prematurely costs far more to repair than the marginal cost of using modified binder during construction. But polymer-modified bitumen is not standard practice everywhere. Cost pressures, procurement habits, and the assumption that historical temperature ranges will continue to apply have kept conventional bitumen in widespread use across regions that can no longer rely on historical temperature ranges. Concrete roads fail through a different mechanism, and understanding it requires a brief detour into thermal expansion. Concrete expands when heated at a rate of approximately 10 millionths of a meter per degree Celsius. That sounds small. Across a long highway slab on a day when temperatures rise 30 degrees, it is not small. Engineers account for this by cutting expansion joints into the road at regular intervals, deliberate gaps that give each slab room to grow without pressing against its neighbors. When those joints are functioning correctly, thermal expansion is harmless. When they are blocked by debris, corroded, or simply worn out after decades of use, the slabs have nowhere to expand. Stress accumulates. It accumulates further. Then it releases. This is the moment engineers call a blow-up, and it is worth pausing to note the irony that the profession uses an explosion metaphor for an event that involves no combustion whatsoever. A blow-up is a sudden, violent, upward displacement of a concrete slab caused entirely by stored mechanical energy. The slab does not burn. Nothing ignites. The force is purely structural, the release of compressive stress that has built past the material's tolerance. The noise it produces, a sharp crack followed by the sound of shifting concrete, is indistinguishable to a bystander from something far more dramatic. In Texas, documented blow-up events have sent slabs of concrete into the air and across multiple lanes of traffic. The distinction between a mechanical failure and a chemical explosion matters enormously for prevention, because the solution to one has nothing to do with the solution to the other. Now consider what happens when moisture enters the picture, because this is the mechanism that surprises people most. Roads are not perfectly sealed systems. Water infiltrates through surface cracks, through joints, through the edges of the pavement. It collects in the granular layers beneath the surface, in the subbase, in pockets within the asphalt itself. Under normal conditions, this moisture drains away or evaporates gradually. Under extreme heat, it does neither of those things quickly enough. Instead, it heats toward boiling. 1 liter of liquid water, when converted to steam at atmospheric pressure, expands to approximately 1,700 liters of vapor. Beneath a road surface that has nowhere to flex, that expansion has only one outlet. Steam pressure beneath an asphalt layer can reach several atmospheres before the surface gives way. When it does, the failure is sudden and audible, and it can lift and fracture the road surface in a way that looks, to anyone nearby, exactly like an explosion. In the summer of 2022, the United Kingdom recorded temperatures above 40 degrees Celsius for the first time in recorded history. Roads buckled and cracked across multiple counties. Footage of warped tarmac and fractured surfaces circulated widely. For a country whose road network was designed around a climate that rarely saw sustained extreme heat, the failures were not surprising to engineers, even if they were shocking to the public. The UK example is useful precisely because it illustrates that this is not a problem confined to places like Arizona or Texas. Any region experiencing temperatures outside its historical design envelope is at risk, and that category is expanding every decade. Soil adds another layer of complexity beneath the road surface itself. Clay-rich soils absorb moisture and swell when wet, then shrink and crack when dry. In a heat event that follows a wet period, the soil beneath a road may be actively expanding upward, at the same time the road surface is expanding outward from thermal stress. The two forces combine. Roads built over clay-heavy ground without adequate drainage or a sufficient load-bearing subbase are particularly vulnerable to this compounding effect, and it is one reason why identical heat events can produce dramatically different outcomes on roads that appear similar from the surface. The factors that turn a hot day into a road failure are not mysterious once you understand them. Extreme surface temperatures push bitumen past its softening point. Blocked or corroded expansion joints prevent concrete from accommodating thermal growth. Trapped moisture converts to steam and builds pressure from below. Clay soils swell and push upward. Aging materials that have lost flexibility crack rather than flex. Any single one of these conditions is manageable with proper design and maintenance. The failures that make news happen when several of them arrive together on infrastructure that was already operating at the edge of its tolerance. That Texas highway from the opening did not stay closed. It was repaired, repaved, and reopened within days. The materials used were conventional. The expansion joints were cleared and resealed. Within 2 summers, a section of the same corridor showed signs of thermal cracking again. The road had been fixed, but it had not been updated. The conditions that caused the original failure had not changed. They had, if anything, intensified. That gap between repair and adaptation is where the real cost of these events accumulates, not in the dramatic moment of failure, but in the cycle of patching infrastructure that was designed for a climate that no longer exists, on a schedule that assumes the next failure is years away, when the physics of the situation suggests otherwise.